can I just clip this to you? Can I just do it to here, or would you prefer it on
I
here?
don't know.
It's a little bigger, but it should be okay. Is that okay?
Yeah, sure.
Originally, Amy was asked to give a lecture here. At the last moment, she couldn't make it. So we found the experimental group. We asked the experimental group to give an improvised lecture on the importance of experimental archaeology in this project. Annemiek Braas.
Good morning, everyone. Well, as already said, we came in last moment with this lecture. And in this lecture, we will talk about some of the experiments that were done during this project, as experimental archaeology was one of the pillars of this project. But in our papers, we generally don't focus on the results, not necessarily on the experiments. So often the experiments don't figure anymore in the final papers, which is sad, I think, because experiments are very interesting and it can be good to see what people have done. As you can see, only Diederik and my name are on the first slide. That's because we put this paper together, but we will be presenting the work of many different people. On every slide with every experiment, we put one person. And that's not because one person helped or did this experiment. With every experiment, there were many, many people joining, helping out, etc. So the person you see on the slide was the person initiating this experiment. So the researcher that came up with the problem is there on the slide. We decided not to put everyone there because it will be a lot of people and also a big risk of forgetting people, especially since so many people were involved. So we decided to do it this way. But I think everybody knows who helped out, that they helped out. And when we were looking at experiments, we saw we could divide them in 3 different kinds of experiments within the project. There were the very large-scale experiments, like the building, the canoe, etc. Those will be presented later today in another paper, so they will not figure in this paper. Then there were some object category-led specific experiments. Because when you're doing research, especially user research and other research, you sometimes come across objects of which remain questionable. You know, you across artifacts of which you don't know how they were used, and you have a theory that needs to be tested. So then an experiment is started. But also some methodological experiments were done during the project, where we look at our methodologies and see what we can improve and how we can improve them and see what... And in all experiments, there's always something happening. And that's the unexpected results. I love this about experiments. When you do an experiment, you always learn something that you weren't looking for. You don't only get the conclusion or the answer to your question, but you always learn more. And especially in this project, there was always an exchange of knowledge. As I said, many people worked on every experiment. So there was exchange of knowledge between scientists, craftspeople, volunteers, and everybody else who helped out in the experiments, and we all learned a lot. And every experiment ever done, I think, also adds something to your view of the past. Because as an archaeologist, you now have a view of the past. You have an idea what the landscape looked like, what the people did, and how they lived. And when you're doing experiments, you learn some more about this. And often you learn that you're wrong, or your views change. And that's also a very important thing of experimental archaeology. Because as an archaeologist, you paint a picture of the past to other people. The visualizations, you give information for visualizations. The pictures taken during experiments also give this information. So experiments work on in changing our view of the past. Well, the first experiment I'm going to discuss is done by Lasse van den Dickenberg. He did an experiment into recycling Neolithic axes. Well, the axes have come along already before in many of the presentations, which will be the case, by the way, with a lot of the experiments that we will be presenting. And flint is not locally available for the Vlieringhen people. So they get it from 70 to 300 kilometers away. 70 kilometers away is just ordinary flint, but there's flint mines at 300 kilometers away, where they also get the flint. For example, Hesbay, Rijkholt and Spien. And as those sources are far away, recycling is an important part of flint technology. And especially the axes. The flint axes in the Vladimir culture were polished. You can see them in the top pictures. And during use, they sometimes break. Like the picture in the bottom right, we have one of the experimental axes that broke during use. It just broke off in the haft. But also in the middle, you see an archaeological axe that was also broken in 2 pieces. And of course, if you're a Vladimir person and your axe breaks, you're left without an axe, which is very sad. But you're also left with 1 or 2 pieces of very high quality flint, because those axes are made of high quality flint. And you can nap those axes into smaller pieces that you can use again. You see some of the pieces on the bottom, and you can see that the polished surface is still present on these flakes, which are generally relatively easy to recognize in your archaeological record, so you know that that flake has been part of an axe. But of course, not all pieces will have this polished outer surface. There's also some pieces that are on the inside of the axe. And how can we recognize them? How can we see how many of those flakes in the side may have been part of an axe? Well, that's why Lasse set up an experiment in which he used 4 axes. 1 axe was already previously used during another experiment and broke, so it were 2 pieces. And 3 axes were especially made for the experiment. 1 was kept whole, and the other was napped into prior to flaking to imitate the end shock, as you also saw with the broken axe in the experiment. All of those axes were then flaked to produce a variety of flakes. So especially to imitate normal use, like to have all different kinds of flake. This was done at Masamuda as a public demonstration to also, of course, connect the public to the materials. And all flakes and all debris was collected. Well, if you have ever seen a flint napper at work, you know that's a lot of pieces, bigger pieces, smaller pieces, and a lot of very small pieces. All those smaller pieces, the debris, everything smaller than 1 centimeter, was sorted to size, and then every single piece that was napped, even the smaller pieces, were analyzed by Lasse and other people who helped them out to see whether they had polished surface. And then the results, they were quite surprising, because 59% of the flakes from the axe did not show any polished surface. So only 41% of the pieces napped from an axe will be recognizable as an axe fragment, and the rest of them are just look like normal flakes. And for the smaller flakes, the smaller fragments, the 1 to 4 millimeter fraction, it was even 79% that show polish, that don't show any polish. So this led to the conclusions that the importance of recycling flint axes on the Neolithic Vladimir culture site was greatly underestimated. Previously, it was estimated that 10 to 20% of the flakes were originally part of an axe, and it's much higher than that. If we look at Hekelingen, where Lasse found 18% of the flakes to be axe flakes, to have this polished surface, that translates to 44 axe flakes if you count in the invisible ones. And in that case, Lasse could also see that some of the flint types, notably the Hesbaye flint, which is also often used for axes, was predominantly imported as flint axes. So the Hesbaye flint was not imported as raw material, but only as axes. Maybe to use as a raw material, but in the shape of an axe. Then we move on to the next experiment by Lucy and others, of course, again. And this experiment looked into how the food crust in prehistoric pottery actually form. Because over the years, Lucy has analyzed many food crusts from many different cultures and very different places, but it's still unclear exactly how these crusts are formed. We find them, but how they come to be there is still the question. So what we did is we had 3 pots that were made with a shape, temper, clay, baking temperature, etc., that were close to the Vladimir material, that were filled with 3 different meals, and we cooked those meals. We cooked them until all the water was evaporated, and when the food crust started to form, Lucy ended the experiment, broke the pots to look at the food crusts. So it's a nice and very good setup. And these are the meals that were cooked. The first one is a porridge-like meal of emmer grain and flax seeds. And you can clearly see there's a charred layer of porridge-like material on the edge of the pot. The second meal was made of crushed acorns, crab apples and rose hips. And also here a thick crust accumulated on the side of the pot. There's a very charred layer and then a food crusty layer as well. And in that layer you can also still see the coarsely ground acorns embedded in the residue, as we used coarsely ground acorns for the experiment. The next one was cooking fish, and we cooked the fish Vlaardingen style, which is just chopping the whole fish or just chopped in rough pieces, scales and all, into the pot. And we cooked that with Gelder roast, as Lucy already mentioned earlier today. First of all, if you look at a personal, I was there with the experiment as well, but also the other people there, it looked gruesome. It didn't look like something you would actually want to eat with those scales and fatty, and it looked really horrible, but apparently that's what we find in the pots. You can also see a very characteristic residue that's accumulated at the rim of the pot, so at the top there and also lower of the scales, and a fatty whitish residue from fish fats. So those were the 3 experiments, and then if we look at the food crust, you can see that the experiment was successful because there were nice food crusts there that really resemble the ones from prehistoric pots. There is, however, a difference. As you can see, the replicated food crusts, they get loose from the pot, so they're not stuck to the pot, but they tend to fall off a little bit, while the prehistoric food crusts are always connected to the pot. The prehistoric food crusts are also cracked, they have a calculate surface, while our experimental food crust didn't have that kind of cracks. So this may be that there was a different cooking method, or maybe the food crust came to be in another circumstance than we created, other accidents happening, or, especially related to the cracks, this might also be a taphonomical process. Then another experiment that already came by in the movie was of a digging stick. This digging stick was found in Vlaardingen, and we could look at it in the museum. That's also why these are our own pictures that are not very nice, because this was made in the museum when we were looking at the object with the root group. And it was originally interpreted as a digging stick. But when we looked at the tip of the stick, the traces there didn't look like we know from experimental digging sticks. So, of course, that warranted an experiment. And I think this is, by the way, a nice example of one of those object-led specific experiments. One object, one question, and a series of experiments. So 3 digging sticks were made by the Masamuda volunteers, using only stone tools, of course, to make the stick look like the prehistoric one. And they were used to dig, as that was the original hypothesis, to stir in a pot, and to soften a fat-tanned deerskin. And here you see the tips of the experimental sticks. And I like this one because you can clearly see the results, the differences. If you look at the digging sticks, you see it's heavily rounded, and that the softer parts of the wood are worn away. So the harder parts are a little bit higher, and the softer parts have worn away a little bit. If you look at the stick that was used for stirring, you can see that the top layer of the wood is worn away. It's lighter, and there's clear scratches visible in the lighter areas. And the last one, the result of softening skin. You see it looks smoother, it's slightly rounded, and there's a polish starting to form. And this actually looked like the stick that we found what was found in Vlaardingen. So the conclusion, it's a small experiment with, in this case, a very nice and clear conclusion that this stick was probably used to soften skin or to work skin during the tanning process. And then we go back to the flint again with an experiment that Lasse did into the flint scrapers that were found. Many of them were used for height working, and there was a variability in the height working because the state of the height, if the height is in a different state, so fresh height leaves different traces than dry height, then deherring, etc. So there's many differences in height working traces, and it had been suggested that some of these traces, some of these scrapers might be used on fatty skins. And the problem is, if skin is very fatty, it's hard to scrape because the fat acts as a lubricant, making it hard to scrape the skin. So it was suggested that maybe they added a mineral additive to facilitate the scraping and making it easier. So 2 seal skins were obtained from the Zeehondencentrum in Pieterburen because seals have very, very fatty skins. And then first the blubber was removed from those skins. One skin they added dry clay, and to the other one they added sand. And both skins were then scraped with flint scrapers. And then we come first to one of the unexpected, but also sort of expected results, that the cutting blubber, because flint blades were used for cutting blubber for 4 hours, and even after 4 hours of use, there was no use wear on those blades. That is because, as I said before, the fat works as a lubricant, and without friction, there's no traces. So that also tells us that if they have ever been cutting blubber in prehistory, we will probably never ever find those traces on flint tools, because it just doesn't leave any traces. They also made incisions in the skin for framing, so to fit it into the frame, and there was polish after 20 minutes. So because the blubber was removed and you cut through skin and hair a little bit, there was polish there. But of course, what the experiment was after was the trace of the scraping. And it created a heavy rounded very heavily rounded edge and a band of polish along the edge. Unfortunately, those traces did not resemble any of the traces on the Vlaardingen sites. And also, there was no clear difference to see between the clay and the sand. So clay and sand leave sort of the same traces. But there was an artifact of, on Schipluiden that was probably remembered by Annelou that had the same traces. So going backwards, we could also, from a site analyzed a long time ago, we did find the match for the archaeological traces. So this gives us new insight in how this can be done, how those mineral additives help or not help in scraping skins, and whether that was done in prehistory. Well, Annelou in her paper already said that I was going to talk about the bone awls, so that's this one. Again, you see only Annelou here, but of course the research was done by many people. And I'm going to find my notes for this one. Because there was several experiments done. When analyzing the bone tools, they found a lot of plant working traces and a large variety of plant working traces, creating questions about how exactly those tools were used. Therefore, it was decided to also use the SEM to analyze those bone tools, to see whether the SEM could help out with the analysis of those use-wear traces. And because the other view, SEM will give another view and another look at the traces than a metallographic microscope, this might help to interpret and maybe distinguish between those traces. And this variety of plant working traces was not only seen between the different awls, but also on the same awls. So they set up experiments to test their hypothesis. Now, together with Ineke Joosten, Annelou looked at with the SEM at the use-wear, and indeed the view was different. And one of the experiments they did was polishing the bone awls with horsetail. Horsetail is known as a polishing agent and also, of course, a material that can be used in craft activities. But in this case, the plant working traces were all over the tool. So not just on the tip, which you expect to be used, but all over the tool. So the suggestion was that maybe the horsetail was used to polish the bone tool during manufacture. And in the experiments they saw, as you can see at the bottom right, you see the traces on the experimental tool, and those traces resemble the traces on the archaeological tool, suggesting this might indeed be a very good option. A second experiment looked at the bone awls. On a lot of the bone awls, traces of grass were found, and they resemble an experiment done by a beehive maker that we have in the lab of a tool that was used for coiling beehives made out of grass. And I'm gonna read this out. Sorry, I'm trying to tell this, but it's not working out, so I'm gonna read out a little bit. On many of the awls, we found randomly oriented striation in combination with a bright polish we connect with contact with grass. These traces bore close resemblance to a tool used by present-day craftsmen making beehives by means of the coiling technique. However, thinking about the practicalities of having these very vulnerable tools lying around in a domestic context, we started to consider storage. And what safer storage is there than having a small container filled with grass, or wool, which we haven't explored yet, to protect the tips. They are easily accessible, and being stored like that, you can imagine that awls were used for all sorts of plants and skins, which would explain the fact that we see the traces from different contact materials on them as well. And there's another one possibility for those awls, especially the one you see here that was found at Hekelingen. That seems to may have been used as a clothespin, because of course a bone awl is also very usable as a clothespin. So an experiment was done where they stuck a bone awl through a fabric made out of retted lime bast to see what kind of traces this left, and of course also the distribution of traces. Because in usewear you don't only look at the traces you see, but also the location of these traces. Because you can imagine if you use a bone awl only for piercing, the traces are only up to a certain height on the tool. When it's used as a clothespin, you expect the traces to be more located in the middle, where it's been stuck in the clothes and been moving around a little bit. If it's being used as a needle or to pierce through material, or there are production traces, you expect the traces all over the surface of the tool. So also the distribution of the traces tells you something about how things may have been used. I'm going to read out a little bit again. Awls have often been considered simple tools, but they can also be used as an accessory like a clothing pin. Its function is not limited to a single use. A clothing pin could also be used as a tool which was ready at hand. To replicate this use, a bone awl was repeatedly stuck into a fabric made out of lime bast. To conclude, it's not strange that every time we looked at awls we saw different traces, which were often difficult to attribute to a specific contact material. These awls probably had a far more complex biography than a simple use on one material. Traces from contact with plants could be related to use, manufacture, storage and transport. And awls could be used in a variety of craft activities, involving materials like hide, bast and of course various plant species. And that also explains how complicated it is to analyze those bone awls, because the tools, the materials used to polish them and to produce them may have been the same as the materials they were used on. And all those traces will get together. So conclusions from the experiments is that the SEM provides another view of the usewear. Polish is less prominent and the surface topography, including striations, are more clear, and SEM therefore provides another view of the traces. And I also heard that, dirt is very visible, much more visible with the SEM, allowing another interpretation for that. So the research with the SEM, usewear with the SEM, is promising and still continuing. So final conclusions about this still have to wait. Well, as already said, all show a complex use. They're not one-time objects. They're used over and over again. And not only used, they're also produced and stored with maybe the same materials. So we know that they did a lot of things with the awls, but exactly what and how is not always clear. Then the last experiment for today is usewear on querns. It has my name, but I also have to mention in this case Tessel de Nijs, who did all of the experiments as part of his bachelor thesis at Saxion Hogeschool. So even though my name is here, I didn't grind anything. And that's, I think, is important to say in this case. And this is a more methodological series of experiments. Because in archaeology we often find much more lower stones than upper stones, because a quern is of course always two stones together. So it has been suggested that maybe they used wood in combination with stone to grind cereals. So that's something we wanted to try out. And of course there's different cereals ground in different periods. And we wondered whether it's possible to distinguish between those different kinds of cereals. We have looked into this before, but we always use different kinds of stones. Because if you are going to do an experiment, you want to use the stones that the people in the past used. So you go to the sources where they source their stone and you get the stones. But of course, because it's all secondary sources, you can't find exactly the same stone. So you can do two experiments on exactly the same stone. That's why in this experiment we used only one kind of stone. I will show you later. And to see whether it was possible, if you use exactly the same kind of stones, if there's a difference between two different kinds of cereals. And also, if you use stone of a wood and stone in combination, do you see traces of those stone handheld current on your use wear traces on the stone? So we used wooden handheld stones in combination with wooden stationary stones and vice versa. You see a big lower stone there made out of wood at the top. And on the bottom you see the very ugly, I have to say, grinding stones that we used for the experiment. There's a simple reason for this. We wanted to use sandstone, but if you want to use the same stone, you have to get them commercially from somebody who works stones. And in the Netherlands, it's forbidden for stone workers to work sandstone because of the dust getting into your lungs, etc. So we had to use granite. So that's why those stones actually look like headstones for graves or kitchen tops, because that's the kind of stone that we used. But the good thing is we know it's the same, because they know from the same source, the same block, so we know it's exactly the same stone. So we use those to grind barley and wheat to see the difference. We also ground barley in combination with other stones and with wood. And we also involved, well, in the end, only one plant material not yet available in a reference collection. But for you, because for use wear you need a reference collection, and we have many plant materials there, but people in the past ate so much more than we have tried yet. So these are the experiments done. They are grouped because it's always a lower stone and an upper stone. And you can see that we used granite, different kinds of wood, and everything has been ground. It has been and also been calculated how much material was processed in the per hour, so to say. And you see there's quite some differences. These are some photos of the objects and tools used in the experiments. Because if you're going to do an experiment like this and you want to grind hazelnuts, you also first have to crack them. So next to those experiments done, there are some extra experiments in cracking hazelnuts, cracking acorns, etc., etc. And here you see some of the traces left. I can imagine if you've never done use wear analysis, they may look all the same. But if you're a use wear specialist, you can see that those traces are clearly different from each other. The top left one is actually the yellow water lily, the other plant we involved in the experiments. And that's very different from the other ones that look more the same. Those are hazelnuts, barley, and acorns. And unfortunately, the first conclusion is that we are not able to distinguish between traces of wheat and barley. So even using the same stone, having a long-run experiment, it's not possible to distinguish between them. So we will always just be stuck with the cereals. And the wooden crunch, we've tried different combination with wooden handheld, wooden lowers, etc. And for most materials, it didn't really work very well. For example, I think it was the barley that was only flattened and not actually ground with the woodens. Only acorns. For acorns, they work better than the stone tools with stone and stone combination. But for the other materials, wood doesn't seem to be an option. And also, a very good conclusion for us was that if you have different kinds of stones for your experiments, the traces don't vary that much. So we can continue the way we are doing with doing experiments with different kinds of stones and reliably using them to interpret the archaeological material. So those were the experiments that I wanted to present to you. And thank you for your attention, of course, but also a special thanks to everybody who helped out with the experiments, because as I said before, there are many others than were visible in this presentation. And a special thanks to the volunteers at Masamuda and the students at Leiden University and Saxion, who also helped out with many of the experiments.
Did it help adding sand or clay in terms of manageability? Could you work more quickly?
Yeah, I think so, but I don't know, maybe Nick knows even better because he scraped so many of the heights.
Yeah, it helped. Yeah. So by adding both clay and sand work well. It helps to absorb and to improve friction on the skin, so the skin's got cleaner. Yeah, definitely.
Could you help me find the photo? Yes, 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 yes.
photo and after that
So the photo was this one, right?
that is the photo.
Sorry, I'm just going to attach this to
Oh, the next item on the program is a film, but before we start that, I want to use 1 minute of your time to make a short announcement. I want to announce the birth of a new foundation, the Stichting Wetland Archaeology. Its main goal is to stimulate and promote thank you, all the archaeological specialisms that do research in the Dutch wetlands. And we aim to consolidate and share all the results so that they will become available to a large public. We started it last week, so we have a very short website now, but more information can be found there soon. Just to announce that we are there. And then the film starts. We have worked with the wood team on the Neolithic wood, and the film speaks for itself.
Oh, I will need to just
Good morning, dear audience. Welcome at Masamuda. We are the wood team, the team that looked at wooden artifacts and wood. Leo Wolterbeek, Diederik Pomstra, Kersti Heijninen, Annemieke Verbaas, very important, but she couldn't be here. And my name is Caroline Vermeeren. We wanted to take you for a stroll around Masamuda to show you all the wood use and the wooden artifacts, but that's not possible. But Yuri is so kind to make a film that it is as if you are walking at the Masamuda area.
In our modern day technology, wood is still an important raw material, but in prehistory it was used for almost everything. Houses were built mainly from wood, but also large artifacts like dugouts and fish weirs, and many smaller objects like household and hunting equipment were made from wood. The bast fibers of the trees that supplied wood were used for ropes, nets, and probably even clothing. Wood was also the most important fuel that fed the fires for both cooking and heating. At the same time, wooden artifacts are a rare find in archaeology. The conservation conditions are important. In archaeological excavations in Western Europe, wood is only found in waterlogged conditions. Since the sites of the flooding culture are often situated in wet environments, excavations have revealed the remains of wooden structures, artifacts, and unworked wood. Nonetheless, we don't find many wooden artifacts. Maybe because of the reuse of the discarded artifacts as firewood. Why waste good fuel? In our research, we used information about the identification of the wood species from literature, and in some cases, they were checked and reinterpreted. We also made detailed descriptions of the artifacts, the woodworking traces and the use wear on the artifacts. This information was not only important for our knowledge of Vlaardingen material culture and wood technology, they also were at the base part of the experimental work that was carried out during the project by Masamuda volunteers. Using all these results together, the team could sometimes make new interpretations.
These are from that period 3 sites that we have investigated. We'll not discuss all of them. We'll give you some of the highlights.
Fibers from tree bast and other plants were used to make ropes and nets. And some examples we could examine thanks to the depot of the Archaeological Bureau of the city of Vlaardingen, VLAK. Because of the fragility of this material, of course, many times it's completely gone and it's hard to recover. But at Vlaardingen Arie Koplaan, some fragments of string and knots were found, which appeared to have been made out of bast fiber. A part of this material is still available, and some pieces of rope and knots may have been part of a net, something like I'm holding in my hand here now. This is of lime bast fiber. We could identify the knots as sheet bends, a well-known net-making knot. A wet and therefore wealth of rope, drawn by Jan for publication. A vulnerable and completely dried and desiccated piece of string we could examine, it proved to be a willow bast fiber. It was difficult to analyze it because the pieces are so very thin, which is a proof, testament of the workmanship. Because the thinner bark strips you use, the finer your rope will be. A hammer made of apple-type wood was found at the Hazendonk, and we had a chance to re-examine it at the RMO Museum in Leiden. Due to wear, interpretation is very difficult. But on the side of the hammer there appeared to have been some long woodworking. There's a piece of bark still left that could have been left as a decoration. We can see that there's a difference in the finishing of both. The short side of the tool is quite pointed, all facets 2 to 5 millimeters wide, as a result of a light, sharp tool, which could possibly have. On the long side, where we would also expect the working production traces, are mostly worn away by subsequent use. The hammerhead is slightly rounded in shape and was used on a relatively as was analyzed by Annemieke Verbaas. Based on the upper and deeper impact traces, as we see, are used on flint, wooden wedges and bone chisels. This hammer was clearly used for hammering softer materials, berries, roots, soft minerals, tendons, dried meat. It's not really clear. No polish was observed, but the piece is very weathered, so polish would be difficult. In the Museum of Vlaardingen, we examined a stick which had a knob on the end and was a digging stick. It's a 61 centimeter. It's slightly bent and oval in cross-section with the narrow inside and the outside of the bend. It is an ash tree trunk or of a thick branch. It has a clear knob, but half of it's missing. The knob is asymmetrical. It's done purposefully. The stick also, the top 20 centimeter or so shows a clear polish, probably of being held in the hand. 20 centimeter has a somewhat darker aspect due to the presence of black deposits inside the wood vessels, a result of charring, but caused by use. The end of the tip itself is shiny, which led on emphasis that it was used for tanning skins. Sometimes use a similar object during the softening phase, when the skin is stretched and tightened in the frame and rubbed. The hypothesis of this tool was tested in 3 different activities with replicated digging sticks. It is digging soft soil, stirring a cooking pot, and softening a fat tanned roe deer skin stretched in a frame. The results clearly showed that the smooth wear and the high polish observed on the artifact could not have been caused by digging, as the soft early wood rings were worn away on the experimental tool, giving the edge a serrated look. The stirring in reconstructed VLC cooking pots also caused this serrated edge, and under the microscope striations were visible that had not been observed on the original artifact. As expected, the results of the height softening experiment most closely resembled the wear traces on the excavated digging stick. In the Vlaardingen site Steinhof, a pointed stick made of juniper branch was interpreted as a cattle herding stick. The stick is 75 centimeters long and only 1 to 1.5 centimeters in diameter. There are many small knots present, partly from dead side branches that were broken off naturally. The living side branches were partly cut and partly torn off. Microscopic analysis showed traces of handling at 2 locations on the stick. The pointed end is slightly collapsed or compressed, caused by pricking or stamping. This use wear is not very pronounced, indicating rare use. The interpretation as a cattle herding stick could agree with this, because cattle doesn't need much pricking and can be herded by arm movements. This stick would then function as an extension of the arm.
Besides reinvesting the known artifacts from this period, we also had the possibility to look at material from samples that were kept in the depots from the Rijksmuseum van Oudheden en de depot van het Vlak, which were samples that were kept for decades and decades, and it was very special that we could have a look in all these old pieces of wood remains and charcoal in the depot of the Rijksmuseum. The samples from Hekelingen, we found torn off branches, the side branches that were clearly torn off from the trees, showing that the wood was not always harvested using tools or axes, but it could also just be torn from the tree. And amongst the samples in Vlaardingen, in het Vlak, we found an object that was not earlier. It was a slightly bent spoon-shaped object, a sort of spatula about 12 centimeters long, only a thickness from 0.2, 0.5 centimeters. We don't know what it is exactly. It's a kind of spoon, so you can imagine things that have been done with that. It's made from yew, from a considerably larger piece of yew, and we'll come back later on the use of yew tree. Beside these known artifacts and new artifacts, we have also been working together on an important, very big item, that is the dugout.
An important item at the Massa Muda volunteer group was the making of a dugout. We had 2 examples for this period in the Netherlands. Both were made of oak. One is from Hazendonk and lies at the RMO, but it's only a piece of the dugout and there is not much detail. Another is from the Wieringermeer, nearly complete and can be seen at the Huis van Hilde. To make a dugout, one needs a straight stem with a suitable diameter and length, preferable without knots and torsion. This means that the tree grew in a dense forest with large trees, which was not present in the area at that time. So VLC people would have to travel to obtain suitable stems. The dugouts were probably made on the spot and only transported after they were finished. Oak is a very durable weed species, and the preference of Neolithic people for making dugouts out of this material is not surprising. Dugouts are constantly wet, and rot is their nemesis. So even though softer, lighter wood species like lime would have yielded lighter craft, the durability of oak wood may well have been a more important factor. Also, oak is difficult to cut and work with relatively short and light flint tools used in the Mesolithic. With the larger and heavier Neolithic groundstone tools, oak is easy to work and shape. Experience shows that oak wood is easier to cut and split with those axes than those softer woods that were used for making dugouts during the Mesolithics. The heavy polished Neolithic axes can be used very effectively on this material. Tool marks from the different tools used on the dugout and tool marks on the wood chips were investigated. Knots can cause problems. If they originate from dead branches, they can fall out and cause a leak. Knots from living branches do not have this problem, but are harder to trim, so less knotty stems is always preferred. In oak, the lower branches often die because of the lack of light, and oak stems for a dugout therefore potentially has dead knots. In the Wieringermeer dugout, a large knot was situated at the front, making this a weak spot. This was solved by creating a hole from 3.5 by 2.5 centimeter that was filled up with a wooden plug to repair the spot. The same modus operandi was used for the reconstructed dugout. Thanks to the Huis van Hilde, we could learn more from the Wieringermeer dugout. For instance, the way that a long crack had been repaired. Over 2 meter, 12 pair of holes were drilled, which had become oval eroded. We used the same method for a bed crack in the Masamuda dugout by drilling holes with a bone drill, sewing the crack together with strong, flexible yew twigs.
Dat het iets soepeler glijdt over het hout heen.
Kun je ook wel over de breuk doen? Als je...
Ja, inderdaad. Ja, dan glijdt hij ook wel makkelijker uit.
Excavation plan of the house shows the post in the center, close to the fire pit. Here, what this may have been, partly because the space around is very limited. As an experimental interpretation, we have chosen to turn it into a work table for cooking. It also makes it possible to burn long pieces of wood in the cooking fire. This saves a lot of hard work chopping firewood with Stone Age tools into small pieces. A bench has been made from the large piece of wood split from the dugout, and above it there's a small attic. On the other side of the fire, the corner of the house lent itself to a sleeping area, and there is a bench along the wall. Many hazel branches were used for wick work of these elements, which were harvested during the felling experiment that will be discussed later. During a wood workshop, an ash trunk was split into planks, which were used to make a cupboard. Pedals were also carved in a wood workshop for the dugout. Of course, there are no archaeological examples of these items, but it's logical and practical, and it works. So that's why we fill it in like this.
To get information about the use of wood in the past and to see if management can be proven, Kirsti, Heinen, Welmoed out, and I have been working on a project to look at modern day trees. We collected data of the yearings and the diameters for about 15 years from several species, and these data form the reference graph for to plot the archaeological data in. And that is another research, but in our project here, we had an opportunity to do a very important experiment, because it turned out that it is quite difficult to find the proof for management in the prehistory prehistoric times. So in the Neolithic, we have data plotted in these reference graphs, but we cannot see a clear proof for management. And that is strange, because we think people had the knowledge and the techniques to do this management. So why is it that we cannot prove it? We have at this moment in that other research, we have a discussion point that it could be that we look at that the excavation types that we look at are different, so that management was not necessary, or it's also possible that a lot of twig-eating animals are around in the woodlands, like the beavers and the deer that eat the sprouting, the sprouts from the trees that were cut. And one of the things that is also possible is that the cutting of the trees with stone or bone tools damage the trees so much that they will not sprout anymore. And that it's not until that you have steel or iron tools that the trees really will sprout. That is what we tried here. Leo and the volunteers have been cut hazel trees that grow near the Massamuda house and near the Vlaardingen.
Are there any questions about the film? No questions. Then our next speaker is Mathilde Siebrecht, and she will present the connections to research in the past.
Yes. Okay. Hello, everyone. Oops, I come to you as a speaker now, so let's see if the technology agrees with me. I'll make it quick, because I know that everyone is staring at the lunch tables. So just to introduce myself, my name is Mathilde Siebrecht. I actually am also a microware specialist. I worked under Annalou, and I worked as a volunteer at the initial house building project at Massamuda. But I come to you today with another hat on as the director of EXARC, which is one of the partners in the project Putting Life into Neolithic Houses. So, very quick introduction. This will be very different to all of the talks you've seen before, by the way. EXARC is the International Association for Experimental Archaeology and Open-Air Museums. The aim is to create a network that connects professionals working in experimental archaeological research, ancient traditional technologies, open-air museum management, and cultural heritage interpretation. And I know a lot of you here today are EXARC members. Lovely to meet you all in person. We have around 450 members from every continent apart from Antarctica, which we're hoping one day to get an Antarctic member. Both individuals, so professionals who are working in various aspects, and also institutions. So for example, the Material Culture Lab here is a member. But so when we came into this project, our role was not necessarily from the research perspective. We've seen some amazing research that has come out of this project so far. Our role was to assist with the communication and the dissemination of the project through various different formats. Hopefully, you will have seen some of these over the last couple of years. We have had some podcast episodes with different people involved in the project. We have a whole playlist on the XArt YouTube channel, where, by the way, the recorded videos from this symposium will also be uploaded, so you can watch them back later. We have various different social media posts, of course, doing things, and we have had quite a few articles in the XArt journal. So that was sort of the way of doing outreach, of disseminating the results of the project. Something, though, that was also very important for the project goals was to connect with present audiences and actually interact with those from outside the project while it was still going on and while it was still being undertaken. So this was hoped to kind of adapt the interpretations as they were taking place, to expand the analysis sort of as the project developed, which therefore was why XArt became involved, because we have this wide reach, and it was really nice to see interactions between not just the specialists in the network and in the project, but also collaboration with those from outside the field. This was done through Kelvin's pictures, which you will hear all about later. We asked for feedback on them, we got some insights into them. So yeah, I just wanted to give a very, very quick talk about why I think that this is really important when studying the past. So of course, as we've seen, we have a wide range of specialists involved in the project, all of whom are very good at what they do, all of whom have potentially very specialized things that they're doing. Maybe some are a little broader, some have years and years of experience, some are new to the field. And the point is that these collaborations are what makes projects like these so successful and allow us to have all of these amazing interpretations that have been shared with us today. By expanding this network out, however, you can fill in any gaps that still might exist because, let's face it, not everyone knows everything. And there'll always be someone who has some tiny little element that they could contribute, or an extra question. I mean, we've had some great questions here today that have already, made us think again about, okay, but no, what about this? And oh, that's a good point. That is something extra that we hadn't considered, or we will be doing that later. So by having other people involved from outside the project itself, by collaborating in that way, it's kind of the ultimate form of open science. And open science is extremely important. It's sort of processes are published as they go. Results are shared before they're finalized, and the wider research community is then invited to share their feedback on preliminary interpretations. Yes. So it's almost a sort of form of friendly peer review and distant collaboration while the interpretations themselves were still being formed. And I just wanted to highlight very quickly, this is very different, I know, from things that we've been talking about before, but I think that projects like this, of course, everyone here is interested in the project. We're all interested in this topic. We're all interested in archaeology. That's why we do what we do. We're not in archaeology for the money and the fame. But the question is always, from outsiders, okay, but why is this project actually important? Why should we give you the money for it? Why is it important to fund it? And so by conducting outreach during the project itself, by disseminating the research in this way, that's something that can help to show the relevance of archaeology to society. I mean, we are currently, there's many issues in the modern world. I put a couple up here. Climate issues becoming stronger, understanding of the human condition is becoming more and more biased by political agendas, borders are becoming much stricter. But by looking at how society has functioned in the past, we can at least make sure that the correct version of different past events is being shared and that people are aware of what happened, so that, for example, things like political agendas cannot take archaeology and use it for their own use. And that's why projects such as this can hopefully broaden modern perspectives and also not just show us insights into the past, but also help us to think about how we actually look at cultures, how we look at societies in the present, and even maybe in the future. So yeah, this was very short. I guess the point that I wanted to make just by sharing this is to say, while of course I think that it's fantastic, the research that's being done here, for me personally, some of the project goals and the fact that outreach was such an important part of it, that collaboration was such an important part of it, is to me one of the most important parts of the research project. And hopefully they can show a good example of the importance of those connections in the present, not just to research the past, but also to actually look towards the future. hopefully they encourage us to keep an open mind to different perspectives and interpretations, and to keep connecting not just within our field, but also outside of it. On which note, I think it is time for lunch and more connections to be built. So, thank you very much. Do you know where the lunch is going to be?